Okay. We have an example of a perfectly inelastic collision in one dimension. We have two carts. They're initially moving with their own velocity, and A is going to overtake B, and they're going to stick together after they collide. And that sticking together and moving with a common velocity is the hallmark of what's the limiting case of a perfectly inelastic collision. So in a perfectly inelastic collision, you're going to lose as much kinetic energy as possible, but still maintain conservation of momentum. For any kind of collision, inelastic, elastic, perfectly inelastic, super elastic, you're going to conserve momentum. Those different categories refer to what happens to the kinetic energy in the collision. Is there more work done on one object than on another object? And some of the kinetic energy is going to be used up doing that work. All right, so some of the values we have for this: the cart A has a mass of 2 kilograms. Cart B has a mass of 3 kilograms. And we're given the initial velocities. So the velocity of A initially is 5 meters per second, and it's moving along what I picked to be my x-axis. The velocity of B initially is given to be 2 meters per second, and that's also along the x-axis. So conservation of momentum is going to tell me I add up all of the momentum in the initial state, and that has to equal all of the momentum in the final state. Because whatever happens in the collision between these two carts, A pushes on B just as hard as B pushes on A. So it's a pair of forces then that are internal to my system. Take the system to be both carts. And internal forces can't change momentum. All right, so let's just calculate what the initial momentum is, and then we'll calculate what the final momentum is. So 2 kilograms times 5 meters per second along the x direction. And then for the initial cart B, it's a little heftier, 3 kilograms, but moving slower, so it gets overtaken at 2 meters per second. And that's going to be 10 plus 6. It's going to be 16 kilogram meter per second along the x direction. The final momentum, I have the two carts stuck together, so it's going to be 2 kilograms plus 3 kilograms, and the unknown final velocity that we want to solve for. So I now know both sides of the conservation momentum, and I have only one unknown. So we can go ahead and set that up. I'm going to have 5 kilogram times V final is going to equal 16 kilogram meter per second along the x direction. So that was P initial. And we can solve for what V final is. Just divide both sides by 5 kilograms. So 16 kilogram meter per second over 5 kilograms on the x direction It's going to give me a velocity of 3.2 meters per second along the x direction. So we got the final velocity, and now it's a perfectly inelastic collision, so I know it's going to have lost some kinetic energy. We actually want to calculate how much was lost. So we're going to add up all of the kinetic energy in the initial state. So part of that was in cart A. So that's a half mv squared for cart A. And then we'll do the same half mv squared for cart B. All right, 36, 25, so it's going to give me 31 joules. In the final state, they're moving together. So their kinetic energy is going to be a half 2 kilogram plus 3 kilogram. And we just worked out they're going to be moving at 3.2 meters per second. You just square that, and that's going to be 25.6 joules. So the change in kinetic energy is not zero. K final minus K initial is going to equal minus, so 31, yep, 25.6 minus 31, going to give me minus 5.4 joules. What that means is that as A was colliding with B and sticking together, A speeded up B somewhat, B slowed down A, but the work that A does on B is not equal to the work that B does on A, and so there's a net amount of work done of minus 5.4 joules. If this were a perfectly elastic collision, then delta K, the change in kinetic energy, would be 0.